Hello, so today we're going to finish up our talk on the periodic table. This is particularly in regards to predicting what types of ions certain elements will form based on the position and location of the and electron configuration on the periodic table, which will become very, very important in the next unit when it comes to chemical bonding. So the first thing we need to explore is kind of where these trends are really based off of, and it's called the octet rule. The rule states that depending on the location of the element on the periodic table, an element will either want to form a positive or negative ion based on the element's tendency to lose or gain electrons to chemically resemble a noble gas. So every element on the periodic table wants to look like a noble gas, and the reason why is because noble gases are inert and inactive. They're stable. Everything in nature wants to be stable. So based off of that, since everything in nature wants to be stable, the elements want to be stable. So what they do is that the most stable elements are the noble gases, and that's the reason why elements want to resemble those electronically. So to do so, the elements need to achieve what's called 8 electrons in their valence electron shell. The 8 is why this rule is called the octet rule, because oct means 8, so it's like the 8 rule. Okay, the valence electron shell is the shell in the outermost highest energy electron orbit that contains the electrons to participate in chemical reactions. So it's the very last orbit or very last orbital in an atom that will want to react with other atoms. And depending on the number of electrons within that orbit, if it has a small number of electrons, it may more likely want to form a positively charged ion, a cation, because it's willing to just let those electrons go. Or if it has 6 or more, it may easily want to gain 2 more electrons to get that 8 in the very end orbital, the very outermost orbital, to have 8 electrons, which if it gains electrons, it becomes negative. So again, we can kind of identify some general trends based off the element's physical and physical properties of electrical conductivity. So this is again in relation to electronegativity and electron affinity. To be conductive to electricity, an element has to have the ability to lose their electrons. The reason why is because to be conductive to electricity, you have to be willing to lose your electrons to allow electricity to flow throughout you. And if you can't do that, then the circuit can't be completed and you're not conductive. Well, we know that metals are highly conductive to electricity, therefore they want to lose their electrons very easily. They want electricity to flow through them like crazy. The reason why is because metals are more likely to form positive ions. They have very small amounts of electrons within their valence electron shell that they're saying, I don't care, just let it go. So that way I don't have to worry about it, and then that means the new shell right beneath it is already full, and it's okay, it acts like a noble gas while its other electrons are floating all over the place like electricity. Non-metals are poorly conductive to electricity because they do not want to lose their electrons, because non-metals, like in the last video, have very high electronegativity and electron affinity. You want to grab as many electrons as possible, hold on to the electrons as hard as possible. Therefore, since they want more electrons, they're more likely to form negative ions. Metalloids and transition metals may form either type of ion depending on what they react with, and we'll talk about that further in other units and stuff like that. But how many electrons do each element gain or lose? Well, we can determine that by reading or knowing how many electrons are in the valence electron shell of each element on the periodic table. So again, this is based on the location of the element on the periodic table itself. For the time being, this rule is only going to apply to the representative elements on the periodic table. So any element that ends with an address of s orbitals or p orbitals is the ones you can really follow this. Transition metals and rare earth metals don't really apply. We'll talk about further what those are in the next unit. So this is kind of a blank periodic table. So what we do is that we start with a valence electron count at 1 on the very far left of the periodic table. So in this column, the alkali metals, they have a valence electron of 1 in their outermost shell. What they're more likely to do is that they're more likely to gain or to lose 1 electron to form a positive 1 charge. So for example, this is hydrogen, and this is lithium. Well, lithium wants to become like a noble gas. Well, the noble gas that comes before lithium is helium, but the noble gas that comes after lithium is neon. So what lithium asks itself is like, would you rather lose 1 electron, or would you rather want to gain 7 to be like neon? Well, elements are lazy, so lithium is like, well, I'd rather just lose 1 electron. So it loses the 1 electron and it forms a positive 1 charge. And all these atoms in this column want to form a positive 1 charge. As you go to the right, you start adding 1 valence electron to the outermost shell. So for the alkaline earth metals, which is the second group from the left, 1 to form 2, same argument. This is going to be beryllium right here. Would it rather lose 2 electrons to become more like helium, or gain 6 to become like neon? It's lazy. It wants to just lose 2. And so that applies to all the elements in this group. Excuse me. Next one, this is the one with aluminum. What would it rather do? Lose 3 or gain 5? It's going to want to lose 3. So it forms a +3 charge. Now, when you get to carbon, the group with carbon, it has 4 valence electrons. So the thing is, based on that, it's in the midway point. Would it rather want to gain or lose 4 electrons? It can go either way in the equivalent amount. So that's the reason why that within this group, they can form both positive and negative ions. So if you find carbon in organic compounds, this is why it makes it so versatile in carbon-based life forms, because carbon can form anions and cations to fit the situation that it's in. So that's where a lot of organic chemistry comes in, is how to manipulate carbon into a state that you really want it to bond both anionically and cationically. So in this case, carbon can form a +4 or a -4 ion. That applies to everything in here. So I believe that's silicon right here. That might be germanium, and so on and so forth. Now, after you get past that, then the tables kind of flip a little bit. So now this is where nitrogen's at. And you have to ask nitrogen, okay, what would it rather do? Gain 3 electrons to become like neon, or lose 5, or lose 4 electrons to become like helium? Well, it's lazy, so it wants to gain the 3. So that's the reason why it'll form a -3 charge. Oxygen's the same way. What would it rather do? Gain 2, lose 5. It wants to gain 2. So therefore, it forms a -2 ion. Then you get to the halogens. They are just one away from the noble gases, so they're easily wanting to gain the 1 electron to become like a noble gas. Fluorine is the most electronegative element on the periodic table. So fluorine forms a -1 charge because it wants to grab all the electrons and keep it to them the best that it can, and it's the atom that holds electrons in the best on the periodic table. So it forms a -1 ion whenever you find it in nature. And then lastly, you get to the noble gases. They already have a valence shell of 8 electrons, therefore their charge is 0. They don't have to form ions. They don't want to form ions. Another way you can kind of think of it, though, let's say I took the representative elements and I kind of set it up in the form of like a mountain. Okay, so imagine that groups 1 and 8 are the bases of the mountain, and then group 4 is the peak of the mountain. So group 1 on the bottom, where it forms a +1 charge. Have group 8, which is the noble gases with a 0 charge. So it's kind of like, again, reading left to right on the periodic table. And then group 4 is right in the middle, and we know that's where it kind of changes, where it goes between positive and negative. Well, then you can kind of just fill everything in. You say group 2 forms +2, group 3 forms +3, and then you get to group 5, and then it forms a -3, and then it forms a -2 for group 6, and then it forms a -1 for group 7. So there's this symmetry in regards to predicting electrons in the periodic table. So you go up +1, +2, +3, and then you get to 4, it's ± -4, and then you go -3, -2, -1, and 0. So if that helps you, you can draw that somewhere. I'd highly recommend it. Otherwise, I mean, if you can memorize this and be able to read the periodic table the normal way, then you can more than welcome to do that. But again, one thing you can kind of notice too, and this is kind of a trick that maybe not a lot of teachers tell you, I'm going to tell you anyway, is that for the representative elements, if you look at the Roman numerals to demonstrate, the Roman numerals demonstrate the number of valence electrons within that particular group of atoms. So if I go to the alkali metals, I know it has a valence electron of 1, which is the reason why it's more likely to give 1 away. And then group 2 has 2 valence electrons based off this Roman numeral. That's the reason why it's more likely to give 2 away. Group 3 has 3 valence electrons and wants to give 3 away. Group 4 has 4 valence electrons. It's halfway between 0 and 8, so it's more likely to gain or lose 4 depending on what it's in. Group 5 has 5 valence electrons, therefore it wants to gain 3 to form 8. Group 6 has 6 valence electrons. That's the reason why it wants to gain 2 electrons to form 8. And then 7 has 7 valence electrons. That's the reason why it wants to grab 1 electron to form 8. And then group 8 already has 8 valence electrons. That's the reason why it doesn't want to grab anything. So the Roman numerals give you a hint to how many valence electrons are in the shells of those representative elements. So it is another trick that you can use to read the periodic table. But besides that, that's the end of this video. If you have any other questions in regards to predicting ions, please come talk to me, because if you don't get this, the next unit is going to suck. I'm just going to say that right now. Chemical bonding is going to suck if you can't predict ions and why certain atoms and elements will form particular ions of particular numerical charges. So if you have any questions, please come talk to me, email me, watch this video over again, stop it, take notes, write questions. You can come ask me later, whatever you need to do. I'm more than welcome to help you out the best way I can. But in the meantime, thanks for watching this video. Hope to see you in the next video and see you in class as well. Bye.